All right, that's a silly song. I always think of They Might Be Giants, Particle Man, when talking about this subject wave particle duality. So I just want to review the learning goals here really quick. Let's see here, my highlighter. Okay, be familiar with the SI units discussed in class. Yep, so that was part of our review. Okay, be familiar with the name constants, Boltzmann, Planck, and h bar, which is h divided by 2 pi. And in this lecture today, you're going to see why we use this h bar constant. Be able to convert energy into various units, kind of as I went through in the first lecture. Be familiar with the four molecular modes of motion and how they connect to the electromagnetic spectrum. Okay. Be familiar with black body radiation, heat capacity of solids, and wave particle duality, including all of those kind of what I would call your physics review, things like interference, diffraction, etc. So it looks like we've finished about half the chapter. We've definitely finished about half the learning goals. However, there's still several more lectures to go. So a lot of these other learning goals are going to take us several lectures to connect. Okay, so I'm going to put that away. And here we go. We're starting with the Schrodinger equation. Okay, so at first the Schrodinger equation appears very simple, almost too simple. As we shall see, it's going to blow up to something very complicated in a hurry. So here's what we have in the Schrodinger equation. So Greek letter psi, okay, psi, technically it's a lowercase psi. That represents the wave function, okay? And we're going to talk ad nauseum about what the wave function is. This h hat, so I'll write like h hat. So that's the Hamiltonian operator, okay? And then E, this is the energy of the system. So the Schrodinger equation is what we call an eigenvalue equation. And so as I mentioned in the previous lecture, there's a lot of German language influence in quantum mechanics. So eigen, that's the Deutsche for single, okay? Single valued equation. And so what does that mean? So what is an eigenvalue equation? And furthermore, what's a Hamiltonian operator? So this is kind of a level of mathematics that is not straightforward. And for many of you, this will be the first time that you're seeing this type of mathematics. So in these eigenvalue equations with Hamiltonian operators, the operator operates on the wave function. Okay, so I'll represent that by drawing an arrow. So the operator operates on the wave function, and it returns, so that's what I'm going to put in place of this equals sign. It returns the energy of the system, which is our single valued component. It's our eigenvalue, okay? So I'll underline eigenvalue and say that is E. Not only does it return the eigenvalue, but it also returns the original wave function. So if you're looking at this and thinking, why algebraically does the wave function not just cancel, right? It's the same as the left and the same on the right. That's because of the mathematics involved in this Hamiltonian mathematics and eigenvalue equations, okay? So what is a Hamiltonian operator? Well, here are examples of a whole host of different types of operators. So we shall see that word Hamiltonian, that's specific to operators used in quantum mechanics. You're already familiar with operators. So for example, the position operator we could call x, so our x scale. And if we apply the position operator, look, it's just multiplying the function by x. So that's what we would do. If we replaced this Hamiltonian operator with the position operator, and we said, you know, x hat operating on psi, then it would return an eigenvalue, and that eigenvalue would be the position, not the energy, but it would be the position because we use the position operator. Or similarly, if we were doing this in polar spherical coordinates, right, we would use r, the radius, okay? So here we can see the momentum operator, and that gets a little bit more complicated. That's negative I, imaginary number, times h bar, times the partial derivative with respect to x. So, and if I continue on here, I'll just describe this. So we can see that's, if it's only in x, if it's in 3 dimensions, you can see we're going to get into some rather complicated math, okay? And then what's going to be most useful for us in this beginning, couple weeks of quantum mechanics is the kinetic energy operator, okay? And you can see that's negative h bar squared divided by 2 times the mass, and the second derivative with respect to position. So the way we would apply this kinetic energy operator is we'd have to follow the order of mathematics. So first, we would take the second derivative with respect to x of the wave function, okay? After we take that second derivative, then we would multiply by negative h bar squared over 2m. And after we carry out that operation on psi, we would get back the single valued, the energy, real number, okay? And we would get back the original wave function, all right? So again, this is mathematics unlike what you've seen before, okay? We also have the potential energy operator. And for now, we notice we're just using symbolic v. V is a function of x. As we advance in the class, we will replace this potential energy operator with an equation. We can also use just a constant. If we had just constant potential energy, then the potential energy operator would be to just multiply that constant by the wave function, okay? And of course, our total energy operator is going to be the kinetic energy plus the potential energy, right? The total energy, okay? So all the same, whether we're using kinetic, potential, or total, we apply this operation on the wave function and we return either just the kinetic energy, just the potential energy, or the total energy, okay? So let's move forward. So now, if I wanted to apply that total energy operator on the wave function, so we can see already how our simple little Schrodinger equation indeed blows up, okay? And so now what we're dealing with for now is the one-dimensional translational motion only, so we're not building in the vibrations or the rotations just yet, and time independent, okay? So this is kind of what we call the standing wave approximation. In a more advanced class, perhaps a graduate school class or in a physics department, you would do the time-dependent Schrodinger equation. And that adds a huge degree of complication. So that's why it is very typical in a chemistry-based quantum mechanics class to look at the time-independent Schrodinger equation as your introductory to quantum mechanics, okay? So how do we get this result? Well, I will remind you, our total energy Hamiltonian operator, okay, is negative h bar squared divided by 2m, okay? Second derivative, and instead of putting a partial, I will just put d dx squared. We're just assuming this is only one dimension, okay? And then that's plus the potential energy. And for now, we haven't put any type of equation, right? We're just using the symbolic v of x, okay? So this is our kinetic. This is our potential. And because this total energy operator, this Hamiltonian, is both the kinetic operator and the potential operator, when I apply this operator through the wave function, notice here now what happens. We have the second derivative of psi of x, okay? I'll put that in a red color, okay? So we first, on the order of mathematics, would have to take the second derivative of psi of x with respect to x, okay? Then we multiply that result, so I'll say times, by negative h bar squared divided by 2m. Also, we have another operation going on, which would be to operate the potential energy operator on psi, which for now, like I said, we haven't put a specific mathematical operation in that yet. And what we would get out of this then would be the single valued, the energy of the system. And we would return the original wave function, okay? So just to walk you through why the kinetic energy operator is negative h bar squared divided by 2m. So recall from classical mechanics. And so anytime I refer to classical mechanics, you know, we're talking about Newton's laws. We're talking about describing cannonballs flying through the air, okay? So we can write the velocity of an object as a vector, okay? Which we know that's dx by dt. So that's the derivative of the position, x, with respect to time. We also know that momentum is mass times the velocity, okay? We know that total energy is going to be 1/2 mv squared, as well as some arbitrarily defined potential energy operator. It could be a constant, like, you know, perhaps I'm holding this object up here, and this, like, you know, this would give me the gravitational potential, which would just be a constant. Or if there was some potential energy that was changing in time or position, we would have to put that operator in place, okay? And so also recall, last time, okay, we wrote, I'm just going to write that KE, we know that that's 1/2 mv squared, but remember that we came up with this last time, that this is really momentum squared divided by 2 times mass for the kinetic energy. And that's going to be far more useful. We're going to see using kinetic energy with respect to momentum, as opposed to just mass times velocity squared, okay? So now I'll remind you our potential energy operators on this previous sheet, right? Negative I times h bar times ddx, okay? So let's write that down over here. So the momentum operator, and I'm going to put this sub x because for now we're only dealing in one dimension, okay? So that sub x is just reminding us this is one dimension. So in that handout, that was written as negative I times h bar times ddx. However, this form is also acceptable. H bar divided by I, no negative sign, okay, times ddx. And I have a little Mathematica notebook open here. I want to show you something. I'm going to remind you, I'm going to be using Mathematica throughout these lectures to kind of remind us of some math that is not so straightforward. So in Mathematica, I can push escape, escape, and that gives me imaginary number I. And we know this has to be imaginary number I, because if I say I squared, let's remind ourselves what we should get. I'll put that up here. So we know that I equals the square root of -1. Therefore, I squared just equals -1. So to prove that we did that correctly in Mathematica, I squared, and there we go, there's -1. So I'm going to show you a rather obscure proof with imaginary numbers. I'm going to write here now 1 divided by escape, I, escape. So 1 over I is -I. This is a weird proof. I'm not going to go through this proof. I'm just going to rely on the fact that Mathematica knows what it's talking about, okay? So that's where we can see these kind of two different forms of the momentum operator negative I h bar d dx or h bar over I d dx. And I kind of prefer this one because I don't have to deal with a negative number at that point, okay? And so then I will also say, because look, we know that the kinetic energy is going to be momentum squared, all right? If I square the momentum operator, okay, and I'm going to square this version of it, that's going to be h bar squared over I squared. And then now that also square the derivative, so I get the second derivative, okay? And now we know that that is going to be equal to negative h bar squared times second derivative with position in x. And so now we can finally see here my kinetic energy operator, which I will, often we see the kinetic energy operator symbolized as T in some textbooks. And I don't want you guys to get too freaked out about all these different letters we're going to use. Some folks use KE, some folks use T. So I'll just try to make sure to communicate the letters. So I'm just going to call this, instead of saying KE, I'm going to write T hat, just so we recognize this is an operator we're talking about, okay? So we know that that's going to be momentum squared divided by 2 times mass. Well, we know just momentum squared is negative h bar squared times the second derivative, and then look, we've got that divided by 2 times mass. So that's where we get this equation from, the negative h bar squared divided by 2 times mass multiplied by the operation second derivative of psi of x with respect to x. Okay, so that's where that all comes from. Beautiful. I think that's what I want to say on this slide. Okay, so moving forward. So now, solving the Schrodinger equation. So solving the Schrodinger equation is no easy task. We will spend half the semester solving the various forms of the Schrodinger equation. Okay, so I'm just going to rewrite that Schrodinger equation that I had up here before. I'm going to write negative h bar squared over 2m, second derivative of psi x with respect to x, potential energy, okay, operating on psi x equals E psi x. And for now, I'm going to assume my potential energy operator is just equal to some constant value. Okay, so we're just going to say constant potential. And I'm going to use the letter V to represent that constant potential. Okay, so now the way that I solve this Schrodinger equation, I have to isolate psi. And I can only isolate psi if an operation allows me to do so. For example, I'm going to first put here, I'm going to try to write this clearly and slow down, second derivative of psi x. So I can't like divide out that second derivative. I have to actually do the second derivative, okay? But I can certainly divide out the negative h bar squared divided by 2m because that's just multiplying by a constant. All right? And so I'm going to say that is now equal to, let's see here. I'm going to flip it because if I wanted to isolate that, I can cancel that. Negative 2m over h bar squared, okay? And now continuing along with this here, we know that E is going to be a constant, and here we've defined V as a constant. So that also means I can separate that operation from psi, okay, through algebraic manipulation. And so I'm going to do a couple steps at once, and I'll just describe what I'm doing. I'm going to subtract the V psi over to that side, and then collect like terms. And that gives me E minus V times psi x. Okay? And so you might be thinking, well, how? You were just telling us we have to do this operation and all that other stuff. Well, look, we're still carrying out all those operations on psi, right? Now, the way that this operation is going to go, it's negative 2m divided by h bar squared times the quantity e minus v operates on psi x. Of course, we would only get that after we take the second derivative of psi x. Okay? And so as it turns out, this is what I'm going to call, I'm going to change color here to make it stand out. So this is a standard second order diffie q. So where diffie q is my little abbreviation for a differential equation. Okay? Differential equation. And second order meaning the second derivative. So a first order differential equation would be the first derivative. A third order differential equation would be the third derivative. Okay? And so as it turns out, because this is a fairly simple form of this equation, and the simplest form of this equation, I'll give it to you generically. So this is d dx of the function f of x equals some constant c times f of x. So that's our standard second order differential equation. And as it turns out, there is a solution to the standard second order differential equation. Okay? And that solution goes as the following. So I'm going to write, here we go, I'll write this, solve. We don't know how to do that yet, but I am going to teach you how to solve second order differential equations. Okay? So it turns out the solution to this thing here, okay, is psi of x equals cosine times kx, where k is a constant, and that constant equals 2 times m times e minus v, all divided by h bar squared, all square root. Okay? So I'll also remind you that in general, when I have this function, cosine kx, this is a standard function of a wave. Okay, so this is a wave with wavelength lambda 2 pi divided by k. So in other words, k is what we call the wave number. Okay? Very cool stuff. Did I leave myself enough room here? I did not leave myself enough room to do the next thing that I want to show. So let's see here. Okay, that's fine. I'm going to go over to the Mathematica now because I want to remind you, I want to show you the connection between this wave number and the wave numbers that we were just talking about in my review lecture. Okay? So if I now define a function, I'm going to say, I'm going to just plot it straight off the bat. Plot cosine kx bracket. And we're going to go from x from, let's say, 0 to 2 pi. End bracket. And I think that's enough to give me a lovely cosine function. Oh, I have to supply a value for k, of course. So what we're going to do is now say manipulate, bracket, comma, and then now we're going to let k go from, let's make it go from 0.1 to 1. End bracket. Lovely. Okay, there is my cosine function. And now I've got 0.1, and I'm going to go in here and put 1.0 for k. So now I've just got Let's see here. Where are we at? Yes. So I've just got a cosine graph, right? A simple cosine graph where my wave number is equal to 1. So I'll remind you, because the wave number, right, is, look, right here, wave number is 1 over wavelength, and we do have that factor of 2 pi in there. So that's 2 pi divided by lambda, all right? A smaller wave number, small wave number, gives me a big wavelength, okay? So let's see how that shakes out here. Oh, you know what I wanted to do? Apologies. I wanted to make this scale all the way up to 10, not to 1. So let's go back to that. Let's go to my, 1.0. And you can probably already see where I'm kind of getting at here, right? So we said a small wave number is a big wavelength. And so now let's look what happens to the wavelength as I make k smaller. Look at that. The wavelength is getting bigger. And so what that also means, the energy is getting smaller. Okay, so small wave number, big wavelength, small energy. On the opposite hand, all right, a large wave number is a small wavelength, which is a big energy. And if I scale now my wave number up larger, you can see I'm getting smaller and smaller wavelengths, which would owe to bigger energies, okay? And so to prove all of this, I'm gonna erase what I just wrote, all of this stuff about k and the wave number, because I wanna make some room here, okay? I'm just gonna add a new slide here at the end. So many slides here. Okay, so here I've just got a blank sheet now. 2 blank sheets. So I'm just going to write here continuation from slide 18. Okay. That says continuation. You heard what I said. Okay, and so what I want to do, that solution that we just came up with, okay, let's rewrite that. Psi x equals cosine kx, where k equals 2m e minus v all over h bar squared and that's all square root. So there's a game we're going to play here, and we're going to kind of go in circles to see if solutions we come up with are confirmed by other solutions, okay? So for example, we recall the de Broglie relationship. So we were working here really with the momentum operator, which is like a part of the kinetic energy operator, right? And we know that the de Broglie wavelength is h bar divided by lambda. So is this solution that we've come up with consistent with de Broglie's wave equation? Okay. And so I'll just remind you that this, when we have total energy, E, I'm just going to write like E total, okay? That's going to be equal to the kinetic energy, EK, KE, T, kinetic energy, plus V, right? Total energy, okay? So then we know that, therefore, and I'm just going to put in parentheses E from our Schrodinger equation, okay? So then we know, doing some algebra here, that E minus V is going to give me the kinetic energy, right? The difference between the total and the potential is the kinetic. All right? So that means I can rewrite this wave number solution up here as 2 times m times the kinetic energy, okay? And that is all divided by h squared and square root, Okay, so if I rearrange now and solve for kinetic energy, I'm going to skip a few steps and just write that directly. We know EK is going to be equal to K squared times H bar squared, all divided by 2 times mass, okay, where we know that that is also equal to P squared divided by 2 times mass, right? So this P squared divided by 2 times mass is another way of writing kinetic energy, right? Which comes from 1/2 mv squared, okay? So now if I rearrange this right here and do some algebra, you can see the 2 mass and the 2 mass is going to cancel. And so I've got K squared times H bar squared equals momentum squared. And of course, I can take the square root of both sides and get K times H bar equals momentum. And this is really cool because recall, you know, K for the solution for the Schrodinger equation, K equals this, 2 mass times kinetic energy divided by H bar squared, all square root. But we also know, right, just from my standard cosine function, that K, the wave number, just equals 2 pi divided by lambda, okay? So now if I substitute that result here, 2 pi divided by lambda, and we also know that H bar is just H divided by 2 pi, okay? Then now that's times H divided by 2 pi, and look at this, this is awesome. 2 pi and 2 pi cancel, and we get momentum equals H divided by lambda. Okay, so yes, the solution is confirmed by the Schrodinger equation. And also we can see this is why we use H bar, because it has that 2 pi unit in it already. And this is going to allow us to make those direct calculations from energy to wavelength to wave number, just like I showed you in the lecture 1 video, okay, reviewing our units, okay? So very cool stuff. So I think that is actually a good place to stop, and I will see you in lecture video number 4.